Now time for a little bit of history. Once Michael Faraday had discovered the principle of induction, experimenters found a way to use a pair of coils to take the low voltage constant output from a battery that was the only voltage supply they had at that time and turn it into a high voltage pulsed signal. So that was used then for a number of things. They called that device an induction coil, and it was used by Hertz to generate radio waves, and it was used by Crookes and Thomson and others when they did work on cathode ray tubes. So the induction coil combines a transformer and a switch. So the way it works is this. The battery, that is a constant voltage but low voltage, is connected to the inner coil that only has a low number of turns. The output voltage is across the outer coil that has very, very many more turns. Now, this wouldn't work, though, if we just have a constant current. We know that transformers need the changing current to make the changing magnetic field that induces the current in the secondary. So they have to make the current turn on and off. To make that happen, a magnetic contact arm was positioned near one end of the coil. And that is shown as the little grey bit just to the left of the rectangle marked A. So as soon as the current was turned on, that coil acts as an electromagnet and it pulls the contact arm towards it. That means it breaks contact with the bit at part A. And so that stops the current and turns the electromagnet off. Then the arm springs back, makes contact again at A, current turns on, and so the cycle is repeated. And this results in short pulses of voltage output at very high frequency. Now you can't call it AC because the current is in fact still in one direction only, but since it's pulsing on and off, the current is changing, so it will work as a transformer. Now, with an induction coil, a 10-volt input could be turned into output pulses that were tens of thousands of volts at their peak voltage. This shows the induction coil that Heinrich Hertz used in his spark gap experiments. You'll often read that he knew the frequency of his transmitted radio waves. The induction coil itself produces pulses over a range of frequencies, but he added a capacitor to the inductor circuit. That means it then oscillates, for reasons which are beyond the scope of this course, at a particular resonant frequency. And they'd worked out from work with capacitors and inductors that the resonant frequency turned out to be omega, which is 2 pi times the frequency, equals 1 over the square root of L times C. So that means if he knew the inductance of his coil and the capacitance of his capacitor, then he was able to find the frequency of the radio waves that his induction coil was giving out. One common use of an induction coil is in a car's ignition coil. When you turn on your car, you turn the key in the ignition, that closes a switch, and then low voltage from the car battery is attached to the primary windings. On the right is a mechanical breaker point, which means that electrical contact is constantly being made and then broken, so that the circuit is switching on and off. So current switches on and off, and every time the current is interrupted, a large voltage spike is applied across the secondary, which is attached to the spark plug.